Alright, Assalamu alaikum. So in this video, we will be studying applications of electrolysis using active electrodes. And there are basically two applications that are really important for us, and that is purification of metals and electroplating. Now, before we start off with the applications, let's very quickly review how electrolysis was done using active electrodes. So firstly, let's recall what an active electrode is. An active electrode is basically when an electrode is made of the parent metal of the salt solution being electrolyzed. So if I have copper sulfate and I'm electrolyzing it using copper electrodes, likewise, if I have iron chloride maybe and I'm electrolyzing it using iron electrodes, then such an electrode would be called an active electrode. However, the same copper electrodes, if they are used to electrolyze iron chloride, or the iron electrodes are being used to electrolyze copper sulfate, they won't be referred to as active electrodes. And now, the principle behind electrolysis using active electrodes was the Champions League. That the cathode larger. And what actually happened was the stepwise procedure was that the atoms that formed the anode, they lose electrons and form ions and move into the solution. Let's draw an apparatus very quickly here. So I have copper sulfate and here's my anode and here's my cathode. So what happens is that the copper atoms that make up this anode, they lose electrons and form copper ions. As the reaction proceeds, more and more of the copper atoms from the rod form copper ions and move into the solution. This causes the anode to progressively diminish. Now, what happens to the electrons that are produced as these atoms form ions? These electrons move into the external circuit and go to the cathode. Here we go. Now what happens is that this cathode is surrounded by a lot of copper ions from the solution. These copper ions come in contact with the cathode, which has electrons on it. And where did these electrons come from? The anode. And these cations combine with the electrons and form copper atoms. So what happens at the anode? Copper is giving us copper ions and two electrons, solid and aqueous. And what happens at the at the cathode? Copper ions gain electrons and form copper metal. So we can see that metallic copper will be formed at the cathode, and therefore the cathode becomes larger. Now you will notice here very evidently that there is no change occurring in the electrolyte. Therefore, we know that copper sulfate is blue. It will remain as blue as it was in the beginning of the reaction. So now that's all. That's all about reviewing what we studied in the previous class, in the previous video. Somehow this is notoriously not going away. It's gone now, thankfully. Right, coming to the applications now. The first application is purification of metals. But let's first do electroplating. Electroplating basically is a chemical procedure. It's an electrolytic procedure in which we coat a metallic object with another metal. For example, you can gold plate a certain piece of jewelry, you can silver plate stuff, and a very important application of electrolysis is galvanizing, which is a way of protecting iron from corrosion. What we do is that we take iron and we coat it with a layer of zinc, which is called galvanizing. Basically, we'll study that when we'll study iron, which I'll hopefully make a video on that sometime later. Uh, so this is basically an electrolytic process. What happens is that we want to, we'll just write this down. It is an electrolytic process of coating a metallic object with another metal. And this can be done for various purposes: for beauty, in case of electroplating stuff with gold, or for protection from corrosion, as was the case in galvanizing iron. So what is our apparatus for this? Now we'll remember this thing, that cathode becomes larger. That means that the deposition is taking place at the cathode. Therefore, the object that we want to coat should always be at the cathode. So let's see. Let's take the example of a spoon. I have a spoon and I want to. The spoon is made of, let's maybe nickel. The spoon is made of nickel and I want to coat it with silver. So because I want silver to deposit at the spoon, and the rule is that it's always the cathode that becomes larger. And why does it become larger? Because deposition is taking place at the cathode. Therefore, the spoon will be kept at the cathode. So the first thing is that the object to be electroplated at the cathode. Now I want to coat this with silver. Therefore, my electrolyte should be a salt solution of silver. So I'll take silver nitrate here, AgNO3, and my anode should be made of the metal with which I want to coat my spoon, that is silver. So here is my silver electrode, which is at the anode. So now let's draw the battery and the connecting wires. Right. So the electrolysis starts. What happens was that the silver atoms that make up the anode lose electrons and form silver ions which move into the solution. Here we have silver ions. And as a result, the anode becomes progressively smaller. The electrons produced move into the external circuit and onto the object that is supposed to be electroplated. Now this metallic object is surrounded by silver ions in the electrolyte. And as these silver ions move to the cathode, they combine with the electrons and produce silver metal, which coats itself evenly onto the surface of the metallic object which we wanted to plate. So what happens at the anode? Ag solid gives us Ag plus and an electron. And what happens at the at the cathode? These electrons are gained by the silver ions. So Ag plus electrons gives us Ag, and which is a solid. So these are the equations. Now there's a condition for electrolysis or for electroplating. Since we want an even coat and we want the object, the coating to adhere to the surface of the object. Like obviously we won't want it to flake off. Therefore, we have to provide a very carefully controlled voltage and current. So what we do is that we provide a low voltage because this ensures that the electroplating process takes time, and when something takes time it's more durable and sustainable. That's a rule of life basically, and this rule carries is just copy pasted in electroplating as well. So we will provide current at a low voltage. So this is a very important condition. Current at a low voltage. Why? Because this ensures an even coat of metal which does not flake off. Even though this process would take a longer time, but in the longer run, it will be more sustainable and more useful and durable. Let's come to the other application, that is purification of metals. Here what we do is that we have an impure metal and we have a pure metal. We want to maximize the amount of pure metal. Therefore, what we do is that we take the impure metal at the anode. So let's draw an apparatus. Let's take the example of copper. The electrolyte would be copper sulfate, pure copper sulfate. And as I just said, that we'll have the impure metal at the anode, and we'll have pure metal at the cathode. Now if you notice here, I have drawn a very thick anode and a very thin cathode. The reason is that we don't actually need the cathode, uh, or we do need the cathode. But the thing is that if you take a look at this reaction or at the reactions that I showed in the previous video, you will notice that it's basically the anode that's dissolving, and cathode is actually just there for gathering whatever is lost at the anode and whatever is required. So we don't really need a very big cathode. We just need a cathode that's thick enough to absorb the stuff, to gather the stuff. So therefore, a thick cathode is not really a requirement. A thick anode isn't a requirement either, but obviously it's more convenient to use a thicker anode so that more of the purification can take place in one go. Now this is the impure metal anode. Now since it's an impure metal anode, it will be having copper ions, copper atoms, and it will be having other impurities as well. I'm drawing these impurities in red. Right. Whereas here we have a pure metal cathode. Now what happens is that the copper metal atoms present in the impure anode will undergo the same process as was happening here. That is, they'll form ions. But the thing that happens here is that we have copper atoms interspersed between impurities. So when they do form ions and they want to move into the solution, they'll have to push their way out from the impurities and then move into the solution. It's kind of analogous to being in a very jam-packed public bus. Your stop has come and you want to move out of the bus. So what will you do? You will push everyone aside and come to the door and get out. And in this process, you will be shaking everyone from their positions. So that's exactly what these copper atoms do. Let's take this copper atom, this one right here. This will form copper ions and move into the solution. Now, as it moves into the solution, it shakes this impurity molecule, this impurity molecule, this impurity molecule. All of these are shaken up. But this copper ion finally succeeds to move into the solution. Now a similar process will be happening to this copper ion, to this copper atom. What's happening? To this copper atom, and they'll all be shaking up the impurity molecules that surround them. As a result of this shaking up by so many copper atoms, these impurity molecules become restless and they start to fall off. So as a result, what happens is that copper atoms from the impure anode start moving to the electrolyte as copper ions, but at the same time, the impurity molecules, because of the force being exerted by these rebellious copper ions, they start falling off and they start accumulating under the anode. These are the impurity molecules. Now, these copper ions that have moved into the solution, they obviously liberated electrons. Only then they would form ions. These electrons moved into the external circuit, and through the external circuit, they reached the cathode. Here they come. Now at the cathode, this cathode is basically surrounded by copper ions. These copper ions came from the electrolyte as well as the anode. So what happens is these ions combine with the electrons present on the surface of the cathode and form pure copper metal. So over time, this cathode would become larger with deposits of pure copper metal, whereas the anode would keep on shrinking. So what are the observations of this reaction? The first thing is obviously that the anode diminishes. Second observation, Champions League, cathode larger. Third observation, this lump of impurities underneath. We call these impurities the anode sludge. So an anode sludge is formed. Now this anode sludge basically has uses, right? And sometimes the examiner likes to ask you, what do these guys do with the anode sludge? Anode sludge is basically made of silicon, or they can be iron as well, some deposits of iron as well. So they can send it to respective industries. Or likewise, this is also used in making roads at times. So these are the uses of this anode sludge. And the fourth observation is that there is no change in the color of the electrolyte. No change in the electrolyte. Now there's one question that you'll often see appearing in the MCQs. What happens is that they'll give you a graph of either the cathode or the anode. So if, let's say, this is the graph of the anode, so what will happen is we'll have mass on one end and we'll have time on the other end. As the reaction proceeds, more and more of copper atoms at the anode form ions and move into solution. Therefore, the anode becomes smaller in size and hence mass. Therefore, over time, the mass of the anode decreases. Mass of anode. Whereas at the cathode, over time, more and more pure copper would be depositing. Therefore, the mass of the cathode would show an increase. Mass of cathode and time. However, the decrease in the mass of anode would be greater than the increase in mass of cathode. Why? Because the anode's loss of mass is accredited to the loss of both the copper atoms as well as the impurities. Therefore, the anode will lose its mass faster than the cathode gains its mass. So that's all about applications of electrolysis using active electrodes. I hope it's clear. If there are any problems, please feel free to ask in the comment section and I'll try to get back to you inshallah. With this video, we are just left with the last topic of O-level electrochemistry, and that is electrochemical cells. With that, Assalamu alaikum wa rahmatullahi wa barakatuh.